All right, let's jump right in. We're going to do a deep dive on one of the most challenging vehicles to electrify, the hybrid cement mixer. And we're not talking about the whole truck. Nope. We're focusing on just one single component that is absolutely mission critical. This isn't just about volts and amps. This is about engineering a piece of hardware to survive in one of the most brutal environments imaginable. Right off the bat, we need a huge shift in how we think about this. This quote, it says everything. If you're picturing a simple power brick, like the one for your laptop, you are setting yourself up for a catastrophic failure. In this truck, the DC to DC converter is the heart valve. It's what keeps the entire 24-volt system, the brain of the vehicle, alive. If it fails, that drum stops spinning, the concrete inside turns to rock, and you've just destroyed a load worth thousands and thousands of dollars.
So to even begin designing this thing, we first have to fully understand the absolute nightmare environment it has to operate in. We're not talking about a nice, clean server room or even a typical long-haul truck on a highway. We are talking about a construction site.
Now, what's really fascinating here is how all these conditions work together to create a worst-case scenario. The truck spends a ton of time crawling at low speeds or just idling, which means you get basically zero airflow for cooling. Then you throw in all that cement dust, which clogs up any cooling vents and literally hardens into an insulating brick of concrete. At the same time, the constant violent shaking from the mixing drum is trying to rip heavy components right off the circuit board. And on top of all that, it's running at over 70% of its max power for hours and hours. It's the perfect storm of thermal, mechanical, and electrical stress. So here's the big takeaway from all this. We are not designing a simple power supply. We are designing a Power ECU, a full-blown electronic control unit that just happens to handle kilowatts of power. It has to be engineered with the exact same rigor, the same safety protocols, and the same obsession with reliability as the main traction inverter that drives the wheels. It's a safety-critical computer that simply cannot be allowed to fail. Okay, so on top of surviving the physics of the job site, we have to navigate this incredibly complex maze of global regulations. Because a successful product can't just work in one market. It's got to be legal and compliant everywhere. And this slide just lays out the headache perfectly. You've got Europe, and they're focused on high voltage safety and making sure your device doesn't emit a bunch of electromagnetic noise. Then you have the US, which is obsessed with post-crash safety. What happens to all that high voltage in an accident? And of course, China has its own comprehensive set of rules. Now, they all share the same basic goals. Don't electrocute anyone, don't start fires, and play nice with other electronics. But the specific tests, the paperwork, the hoops you have to jump through, they can be wildly different. So the strategic answer here is crystal clear. You absolutely cannot afford to make a different version for Europe, one for America, and another for Asia. The cost would be insane. The only smart path forward is to design to the strictest possible combination of all these global standards right from day one. You design it once, you get it certified everywhere. All right, let's get into the core technology. This is without a doubt the single most important technical decision you will make in this entire project. It's going to dictate everything: performance, size, weight, and of course, the final cost. So we're basically looking at two choices. On one hand, you have traditional silicon MOSFETs. They're the old guard, proven, super reliable, and cheap. On the other hand, you have the newer tech, Silicon Carbide, or SiC. Now, SiC is a game changer. It switches much faster and way more efficiently, which means less energy gets wasted as heat. And because it can switch at a higher frequency, all the magnetic components, the transformers, the inductors, can be much, much smaller. So the whole unit gets smaller and lighter. The catch? Well, the SiC chips themselves are a lot more expensive. But here is the critical verdict from the analysis. That higher upfront cost of silicon carbide, it's an illusion, because when you zoom out and you look at the total cost of ownership over the truck's entire life, SiC is the clear winner. You get a smaller cooling system, a lighter chassis, and most importantly, real fuel savings from that higher efficiency. For this kind of high-power, long-running application, it's a no-brainer. And this is exactly why it matters so much. That 1 or 2% gain in efficiency isn't just a number on a spreadsheet. For a vehicle that is running all day, every day, that tiny percentage translates directly to a 1 to 1.5% drop in fuel use while the mixer is running. Now, multiply that by a whole fleet of trucks over 10 years. We're talking about a massive savings in operating costs. Okay, so we've chosen our core technology. Now let's get into the nitty-gritty of building a physical box that can actually survive out in the wild. This is where we design for indestructibility.
First up is cooling, and let's be real, it's not actually a choice. As we already saw, air cooling is a total non-starter. It doesn't work when the truck is moving slow and gets clogged with cement dust. So a sealed, liquid-cooled system is the only way to go. It's totally immune to dust, and it provides rock-solid cooling whether the truck is on the highway or stuck in traffic. It is absolutely mandatory for this to work, period.
Now let's talk about sealing, because this is just on another level. The rating we need for all the connectors is IP6K9K. This is not your standard waterproofing. This rating means the component has to survive being blasted at point-blank range with an 80°C high-pressure jet wash, day in and day out. It's a test specifically designed to mimic the aggressive chemical steam cleaning these trucks get every single day. And to fight that insane vibration, we follow a simple 3-step playbook. First, you start with a thicker-than-normal printed circuit board as your foundation. Second, you take any big, heavy components, like transformers, and you mechanically bolt them directly to the housing so they aren't just hanging on by their solder joints. And third, you encapsulate critical areas in what's called potting. Basically, you pour in a hard epoxy that locks everything into a solid block. This completely stops the tiny vibrations that cause solder joints to crack over time. Finally, this whole design has to be done through the lens of functional safety, or ASIL. This is a very formal process for figuring out what can go wrong and building in backups to prevent disaster. For our converter, that means we're designing to ASIL B as a minimum. But if this box also powers something critical, like the electric power steering, then you have to jump to ASIL C, which demands even more redundancy to make sure no single failure ever leads to a loss of vehicle control.
So, we have the complete technical blueprint. We know exactly what this thing needs to be. The final question is a strategic one. Who is going to build it? And this brings us to the classic build versus buy decision. If you build it in-house, you get total control. You can make it perfect for your needs. But the development costs are massive, and so is the project risk, especially if your team hasn't done this 10 times before. On the flip side, you can buy it from a specialized Tier 1 supplier. It's way cheaper, it's faster, and you're basically outsourcing the risk to them. The trade-off? You give up a little bit of that technical control, which leads to the final strategic recommendation. For your first-generation truck, play it smart. Mitigate your risk. Partner with a Tier 1 supplier who already has proven experience building heavy-duty, liquid-cooled power electronics. Let them handle the complexity. This gets your product to market faster and with fewer headaches. Then, you can use that experience and potentially bring the design in-house for Generation 2. It's a phased approach. You walk before you run. And so it all comes down to this one question. Your entire hybrid vehicle program could depend on this one component getting done right and on time. Where do you place your bet? Do you gamble on the potential of your own team to figure it out as they go, or do you trust the proven experience of a seasoned expert who has already solved these exact problems? It's the ultimate choice between risk and control.